Hello students! In a previous video, we learned about irrational numbers. We also learned that irrational numbers are those numbers which cannot be written in their P upon Q form, while rational numbers are those numbers that can be written in their P by Q form. We also saw that rational and irrational numbers together form a bigger set of numbers called real numbers. Students recall that any positive integer, which is also a real number, can be expressed as the product of its prime factorization to its simplest form, known as prime factorization of real numbers. Any prime number is a natural number greater than 1 that is not a product of two small natural numbers. Now, alternate but equivalent definition of prime numbers is they are the numbers with exactly two positive divisors, 1 and the number itself. For example, 5 is a prime number as it can be written as 5 equal to 1 into 5, or 5 is divisible by 1 or 5 itself. But 4 is not a prime number. You already know that 4 can be written as product of 2 into 2, or 4 is divisible by 1, 2 or 4. In this video, we will prove that if any prime number p divides square of any number n, then it divides the number n also. In other words, if prime number p is a factor of n square, then it is a factor of n also. Students recall that factor can divide number completely or evenly. In theorem, this can be written as let p be a prime number. If p divides a square, then p divides a, where a is any positive integer. First, let us understand theorem by these examples, and then we will see its proof. Let us take a as any number, say 16. Now write its prime factors. Can you? Yes, it is 2 into 2 into 2 into 2. Now make square of 16. We get 256. As per theorem, divide 256 by prime number 2. We will get quotient as 128 and remainder as 0. Thus 2 divides 256 evenly or completely. So we can say that it is a factor of 256. Now students, divide 16 by 2. What do we get? Yes, you are right, we get answer 8 and remainder is 0. Thus we can say 2 is a factor of 16 also. Similarly, if we take other number, say 21, and write it square, we get 441. Now divide 441 by prime number 3. We get answer 147. Now divide its root, that is number 21 itself, by 3. What do we get? We get answer 7 and quotient 0. We see that 3 divides both a square and a in this case. Now try this with number 25 by yourself. What do you observe? You'll find that both 25 and its square 625 is divisible by 5. Thus we can say that if any prime number divides square of the number, then it will divide number also. Now let's prove this theorem. For that, we write statement, given, and to prove of the theorem. So we are given that let p be a prime number, and if p divides a square, then p divides a also, where a is any positive integer. So we are given that p is prime number and it divides a square. It is a factor of a square. And we have to prove that p also divides A, that is, it is a factor of A also. Now students, no assumptions are required to prove this theorem. So we will directly start the proof. Let us take any number A and write its prime factorization as P1 into P2 into P3 and so on, where P1, P2, P3 and Pn are prime factors of A. They are not necessarily distinct. Some might be repetitive numbers. Let us take squares on both the sides in equation 1. So we get A multiplied by A, which is equal to A square, which is equal to P1 into P2 into P3 and so on, multiplied by P1 into P2 into P3 and so on. We get A square is equal to P1 square into P2 square into P3 square and so on. Now it is given in the theorem that P divides A square. So P is a factor of A square. Now recall fundamental theorem of arithmetic. This theorem states that every integer can be written as a product of one or more primes. The prime factorization of any number A is unique except for the order if the factors and the factors are all distinct. In simple words, any two prime factorizations of same number will have same numbers of copies of same primes, although their order may differ. Prime factorization of one number will never be same as prime factorization of other number. Therefore, according to fundamental theorem of arithmetic, P is one of the prime factors of A square, since it divides A square. Or we can say that P belongs to P1 square, P2 square and so on. Now, by uniqueness of fundamental theorem of arithmetic, we can say that P1, P2, P3 and so on are the only prime factors of A square. This implies that P is a part of prime factors of A, that is, it is amongst P1, P2, P3 and so on. But we also know that P1, P2, P3 are also the factors of number A according to equation 1. So we can say that P is a factor of A also. Since it is a part of P1, P2, P3 and so on, hence P is a factor of A. And if P is a factor of A, then it should divide A completely or evenly. So we can prove that if P divides A square, which we are given, then it will divide A also, which we have proved. So students, this theorem says that if any prime number is a factor of A square, then it will be a factor of A also. Students, remember this theorem because we will use this theorem to prove another theorem in our next video. In the next video, we will see theorem 2, where we will prove that square root of any prime number is always irrational.